So let's have a look at some exam type questions where we use the Arg diagram and modulus argument form to solve the problem. So the first one is, the first part's pretty easy. So express 1 plus I in modulus argument form. So we know that 1 plus I would be the square root of 1 squared plus 1 squared gives us 2 as our modulus argument. And we know that the point's actually in 1 across, 1 up. So that would give us an argument of pi on 4, 45. So we can write it as that form. Root 2 says pi on 4. So there's 1 plus I in modulus argument form. That's the easy part. So the next one is, we're told that 1 plus I to the power of n is equal to x plus iy. So where that's just going to give us, put it to the power of n, you're going to get some complex number, x plus iy. Makes sense. Where x and y are real numbers and n's an integer. So what we want to prove that x squared plus y squared then would be equal to 2 to the power of n. Okay, well, let's have a look. We've got 1 plus I to the power of n. Now what we're going to do to use that, we know that 1 plus I could be written as 2 to the power of a half, or square root of 2, cos of pi on 4 plus I sine pi on 4. Because we know that 1 plus I in modulus argument form was like that. Now that starts to make life, we put it in that way because it starts to make it easier to put it to the power of n when we remember de Moivre's theorem. Remember de Moivre's theorem was we took a complex number and we put it to the power of an integer or a number, and that would be r to the power of n times cis the power cis of n theta, which is cos n theta plus I sine n theta. So when we do that, we are able to get this situation. So 2 to the power of a half to the power of n gives us 2 to the power of n on 2. We just multiply the powers. So that's why we get n on 2 there. And remember, we get cos, the argument just gets multiplied by n, so it would be cis of n pi on 4. Now I've written it in shorthand way, but you could write it as cos of n pi on 4 plus I sine of n pi on 4. So if that's going to be written as a complex number, so x plus iy, the x part then would be equal to 2 to the power of n on 2, which was the argument at the front, times cos of n pi on 4, because that's the real part, is cos of n pi on 4. And the y could be written, because it's going to be I sine n pi on 4 there, so we get 2 to the power of n on 2 times sine of n pi on 4 as being y. Okay, so what happens if we square that? So we get x squared is 2 to the power of n on 2 all squared would give us 2 to the power of n. And then we just got this angle, and it's going to be squared, so it's going to give us cos squared of n pi on 4. We can't put the 2 times that because it only works for de Moivre's theorem when you're doing it with cis of pi. Cis of theta become to the power of n becomes cis of n theta. It doesn't work this time because it's just cosine by itself. Y squared would be that part that we just had there, we said was equal to y, and we square that, again we get 2 to the power of n and sine squared of n squared and n pi on 4. So if we're going to add these two parts, we add these two parts. So 2 to the power of n, well that's common, so we could factorise it out. Then we get cos squared of n pi on 4 plus sine squared of n pi on 4. We remember that cos squared of an angle plus sine squared of that same angle would give us 1. So all that part's equal to 1. It's going to leave us x squared plus y squared equals to 2 to the power of n. So nice little way to do that. One a little bit easier. If z is 3 plus 2i, graph on the Arg diagram, z plus the conjugate of z, well we know z's 3 plus 2i, conjugate would be 3 minus 2i. Remember, conjugates are reflections. And we can, I times z, well if we do our multiplication here, we get I times 3 plus 2i gives us minus 2 plus 3i. So we would get that there. So there's the 3 minus 2 plus 3i. Notice it's 90 degrees. So you can see when you plot that out that you get that situation. What about z plus iz? So in this case we get 3 plus 2i, which was z, and we're going to add minus 2 plus 3i, gives us 1 plus 5i. So there's 1 plus 5i there. So that's the multiplication of z times its conjugate, times 1, the 1 plus I there, times another complex number. So it's going to give us that diagram, that point there. So it's distance there at a different angle. So we'll do more with that later on, with those type of things with our work next week. Z is 1 minus I, W is minus 3 plus 3I. Find the argument of Z plus W. Well, if we add them together, we get minus 2 plus 2I. So again, we're going to go back to the idea of where's minus 2 plus 2I. So we go across 2, up 2. So it's going to be minus 2 plus 2I there. So we're looking at that angle there. We can get that angle, which would be inverse tan of 2 on 2, which is pi on 4. Gives us an angle of to the line from 0 of 3 pi on 4. So there's our argument of Z plus W. Question 4 here. This one's an interesting one. You can do it in a number of ways. If we consider x plus iy to the power of 3 is equal to 1. So basically saying you get a complex number, you cube it, you get 1. So that's what it would be. So we want to show firstly that the modulus of x plus iy would be equal to 1 as well. So if that's the case, basically we would say, well, x plus iy would be the cube root of 1, which would be equal to 1. That would be one solution. Remember, if we've got a complex number cubes, or taking the cube root of 1, there'll be 3 solutions for the cube root of 1. There'll be 3 numbers that multiply to give will be able to be cubed to give you 1 because in the terms of a complex number. So one of them would be 1 because that's the most simplest result. So if that's the case, what we would get is that's a complex number that would be x plus iy. So that's the most simplest one. But if we have a look at that, the modulus of all of them would be the same. So that's got a distance from the origin of 1, which means x plus iy would equal, the modulus of x plus iy would equal the modulus of 1, the number of the point 1, or the complex number 1, which means the modulus of the complex number 1 would be 1 as well. So the modulus of x plus iy would equal 1. So that's going to lead us into the next part, was like solve this equation. So what we're looking at, the idea is that we know that the modulus is 1. We saw that. Doesn't matter what the complex number. As we said, there's three complex numbers that are going to give us 1 there. And when we cube them, okay, and we know one of those would be 1 plus 0I, because that we just saw that. What we're going to do though is use de Moivre's theorem to help us solve this. So we know that if we looked at x plus iy to the power of 3, now by de Moivre's theorem, we could write that as a complex. Basically, that in this terms, like 1 was our modulus, and we could write it as cos theta plus I sine theta. So if we cube this one, we get a 3 in front of each because by de Moivre's theorem. So cos 3 theta plus I sine 3 theta is equal to 1, which basically means we're going to get 3 different angles that's going to be able to work in there, and it's going to give us 1. What we know is that that's really 1 plus 0i as well. We could write that as a complex number. So cos 3 theta would be equal to 1, and sine 3 theta is equal to 0. So where does those two situations exist at the same time? Well, we know that again, consider the idea that our domain is 3 theta. We know that 3 theta must be between 0 and 6 pi, because theta is between 0 and 2 pi. So that would mean 3 theta could be either 0, 2 pi, or 4 pi. So what we're saying is, when we get onto the positive x-axis there, we know we get sine of an angle being 0 and cos of an angle being 1. That's the only place where that happens. Sine of this angle here is 0, and cos of this angle is 1 every time. 0, 2 pi, 4 pi is equal to 3 theta. So theta then would be 0, 2 pi on 3, 4 pi on 3, which means that we knew that was going to be the case. One of the answers would be 0. So we know our modulus was 1, was the modulus of one of the, we proved in part A from part 1, or part A was 1 as well. So we know it's going to be 1 cis theta, which cis of 0, which is 0 anyway. or cis of 0, and one cis 2 pi and 3, and one cis 4 pi and 3. And writing those ones in this form, we can see that cos of 2 pi and 3 is minus a half, sine of 2 pi and 3 is minus root 3 on 2, cos of 4 pi and 3 is minus a half, cos of sine of minus sine of 4 pi and 3 is minus root 3 on 2. There's our three solutions, and we can see that in a diagram as well. Now we can see if we drew them up, and this is what basically we've done. What we call this is the cube roots of unity. So we've taken the cube roots of 1, and with the complex numbers, that's going to give us 3 numbers. Every time you take them, if you took the square roots of unity, you're going to get 2 solutions. The 4th roots of unity, we're going to get 4 solutions. The 5th roots of unity gives us 5 solutions. Again, this is something we'll look at in the next couple of weeks in a bit more depth. But we can see that when we get this, the 3 numbers we've got all have an argument of 1. A modulus of 1. So the distance from the origin for all 3 is 1. And they're equally spaced. If you have a look, they're equally spaced around the circle at 2 pi and 3, and that's not just luck. That happens, and that's where we're going to get those. The other way we could have done this is to find out, say, well, z cubed equal to 1, z cubed minus 1 would equal 0, so we get z is equal to z minus 1, and we get the factorization z minus 1, z squared plus z plus 1. So z minus 1 would say, well, z must equal 1. Well, there we go, that's z's equal to 0 plus minus 1. If you solve this one by the quadratic formula, you won't be able to do it any other way. You'll get those two. So you get these 2 solutions from that one, and you can do that for yourself and have a look. But that's what you're going to get. So there's your 2 other cube roots of unity. Again, we'll do more in the next couple of weeks on that. So this one, let z be equal to 8 minus I divided by 2 plus I. Express z in the form a plus ib, where a and b are real numbers. Well, we did that the other day. Last week we were able to multiply by its conjugate, get down to that number, and then hence our other find argument of the modulus of z and the arguments of z. Well, now that I've got down to 3 minus 2i, I'm able to substitute those to get the modulus, and the argument would be inverse tan of minus 2 pi and 3, and it's 3 minus 2, so it's in the 4th quadrant, so that would give us an angle of minus 33.7, or in radians, minus 0.588, which is what they wanted. They want us 3 significant figures in the domain between minus pi and pi, so we have to come down to that. Given that z's 1 minus I root 3, put it in modulus argument form. Again, what we've been doing, getting a modulus, arguments in the 4th quadrant, so we could write it as 2 cis minus pi and 3, or 2 cis 5 pi and 3, whichever way you get it. And hence find z to the power of 8. Well, it starts to make life a lot easier. We're able to put it into its modulus argument form and use the Moivre's theorem. So 2 to the power of 8, and cis of minus 8 pi becomes minus 8 pi and 3 now, which again, minus 8 pi and 3 is 2 pi and 3. It's in the same spot, it's in the same position, so we just bring it back to its principal argument. 2 to the power of 8 is 256. Cos of 2 pi and 3 would be minus a half. Sine of minus 2 pi and 3 is minus root 3 on 2. Multiply both those numbers by 256, and we're able to get back in that form. So it's much easier to go, rather than trying to expand that out using a binomial expansion. Could be done, but it will take you lots and lots of lines to do that. Much easier to convert to modulus argument form, which we did in part 1, then use de Moivre's theorem, then convert it back from modulus argument form into the real part and the imaginary part to be able to solve that question. So there we go. There's how we solve a number of those questions using the modulus argument form. You can, hopefully you're starting to get the idea that it's really powerful, especially when we're multiplying, dividing, or putting something to powers of large numbers.